And we start recording. So, like I said, just briefing for anybody who's catching us on videos. If you have questions with the video I posted last time, come talk to me. Yeah. And it is very helpful thing to understand this. That's actually the, is it part of NP complete problems before? Okay. Right. This is actually considered the biggest, or one of the biggest open problems. Um, our non-deterministic Turing machine polynomial atomic algorithms, is there a standard way to convert them into a deterministic machine's polynomial atomic algorithm? This is the P versus NP. And that is one of the 7 what we call millennial problems. So one of the 7 great math problems for the next century that they did a similar thing in the right at the 1900s. They announced these great problems in mathematics. One of which was, can you come up with a machine that can prove outcomes? And that's what eventually resulted in the whole work with Gödel's theorem and the building of Turing machines, which led to computers, all sprang from that. This is kind of the follow-up. How can we tell some of these? There are some problems that prove to be particularly thorny. Okay? And that's one of the categories is NP. There are other categories. There are worse ones than NP. But NP is a very broad category. It hits things we care about, like how do you design circuits? How do you plan trips so that you can get an efficient trip? And things that they all turn out to be the same stupid problem you need. Right? So if you solve one, you solve all of it. It's a huge thing. Encryption, decryption, the cryptocurrencies, searching, all run into the same attack. So it is a really big fundamental problem. You've all probably heard complexity, right? Or complexity classes, maybe. Yeah. Um, this is intimately tied because NP is one of the complexity classes. Yes. At least for all. So anyway, this is a lot of what we're talking about, these type of areas. And this is where we kind of strike it on the area. So this is, it's big, it's really cool. It's where math and engineering and computers intersect at the cutting edge of the world. Anyway, we're going to move on to another very fun problem that for a while, I'd say almost like maybe 10, 15 years ago, I almost considered dropping the asynchronous stuff that we're doing. It's neat. It has some limited applications. One of the big advantages is speed. But then in more recent times, there's been a need for these and they started creeping back up. And people have talked about asynchronous computers and other stuff, as it can be very helpful for some machine learning things and stuff of that sort. So it looked like it was going to go away, and then demand for it crept back up. And I'm like, okay, well, you can't drop it again. So you'll notice this throughout your life. Certain topics will ebb and flow with current needs. So I still think it's a pretty vital one, actually becoming more vital in many respects. So let's talk a little bit about what we mean for synchronous versus asynchronous. Yeah, I can spell. Okay, what do you mean by synchronous before we get to asynchronous? Anybody know where the word comes from? What's that? Same time, like they're together. Okay, so it's technically, so you're right on, right? Chronos is time, right? It comes from the ancient Greek Titan, who all this kind of stuff, right? Chronos, who was, he was basically the one who was, his powers were time, right? So chronos, right? Chronographs, chronographies, chronology, all this goes back to those type of things. An old name for a watch was chronograph, right? So, syn meant with, right? So synchronous meant with the same time. So they were taught. To our term, that's what it means, right? It's got a clock. So there's a clocking signal. So that exactly what you're saying is the eventual result of this, that these things are forced to happen at the same time, right? So that's why synchronous is important. What is asynchronous? What is it? When you put a in front of a word, what does that mean? Yeah, not, right? It's, again, this is Greek, right? So if you put an A in front of something, it means not. So asynchronous means there's no clock in our terms. We don't have a clock that's timing these things. Now, usually when we say synchronous, we don't just mean that there's a clock, we mean a particular thing about that clock. Does anybody know what that particular thing is we mean about having a clock for a signal?
It's not like consistent. It's not consistent 1-0.
So actually we do with synchronous, we want a very consistent one.
Yeah.
Right? So we actually do crystal oscillations, right, on that. And we'll show you another way you can make, a similar, a time signal, right? I can also do an electric circuits oscillating. The problem with the electric circuits is they heat up. And once things heat up, they change time. They change how fast the gates transition by temperature. So as you run it, your timing changes. That's kind of annoying. It doesn't change with the crystal oscillation. Right? So low in energy input, it very rapidly reaches a constant, and then that oscillation is very smooth. We often will then encase it inside more cases and things of that sort. Because we don't want outside energy messing with it. And, right? We do vibration damping, all kinds of things, so that we can keep those crystal oscillations very consistent. So we do want a very consistent clock when we do synchronous. But we usually mean we're trying to say we know a particular instant in time. So when you look at consider a clock signal, and imagine I can draw a consistent square wave. It's actually varying. That's just a distortion. I can actually draw them perfectly. Unfortunately, the paper cannot capture my purpose. Yeah, no, I can't. There's a reason I'm not an artist. I'm an engineer. But imagine that it was a perfect square, exact pointing, all kinds of stuff, right? At what point along that clock signal can you tell exactly an instant? Yeah, only the edges. Only the rising edge or the falling edge or both. But otherwise, if you just consider when it's one, there's a whole bunch of intervals right next to each other. Right? So it still has a continuous. We mean with synchronous, we want to go to truly discrete time, and we want edge triggering. And that's really nice because it's safe. Right? You know exactly when it is. It only samples that one instant, so you can't get bad behavior. Right? So that's nice. It is safe. It fixed a lot of our problems. So why would we ever want to move away from such a safe, reliable, nice system? It's easy to use, all kinds of things.
It's, it would be because we want to spend something else tangible that is the edges. So somewhere else but in one see. So if you were using a sync system, we have to wait and cause delays. So with an A thing, I'm imagining it would have flags and triggers and we would change things and say, okay, at this time this.
Okay, so this is one issue that you can go into, right? What happens now? In the best case, you get a delay from when the event happens. Imagine for a sec though, you get hired working at Stern, pick your favorite, right? So I've got, in a bench, you're working at the Large Hadron Collider, you're working at any one of these ones. Do you know exactly when the impact is going to happen between the particular subatomic particles striking the, atomic target to create or release the, particles and energy?
You can test.
So those, yeah, and this is kind of the challenge, right? So now I get this really fast delta spike, right? Because a lot of these particles are only going to exist for like, a tiny fraction, probably even the only picoseconds type of thing, maybe even less, right? Some of these things are so unstable, they're even like femtoseconds and crazy stuff like that. So this is a tiny spike. Now you're coming along with this tiny, tiny spike, and you're putting in some sampling thing. Right? Here's my time axis, and I'm sampling like this. Right? See that? See, this is the problem. I'm only letting the input in at those instants. So you stand no chance of being able to find it. Um, I've actually known some people who not with not so drastic thing, maybe well, in the case of a nuclear accelerator or something, maybe I care. I've known people who have had weird intermittent problems in their car electrically, and it didn't show up on the particular oscilloscope that the mechanic had because it was happening so infrequently for this little tiny spike. Right? And when they went to a mechanic who had a better that could sample a high frequency, all of a sudden it appeared. Right? So this person literally had this weird electrical thing that was going on, and it just didn't show up because it was being sampled that too slowly. Faster sampling actually was able to find the spike. Right? But you can imagine it's not. I do a lot of manipulation. I am using accelerators and stuff, but I have to sample these in accurate time. We have to do triggers that are not based on clock. Because no matter how fast you trigger this dumb thing, you might miss the particle. Um, That's another. So there are tons of these cases. Something coming in at a weird interval time would be one of those key spots, right? That you don't know when the timing is going to happen.
So this also play into like real time effects that we need.
So the question is, what do you mean by real time? Most people, like if you talk to a general person out there, real time means fast, and it's actually happening. As engineers, that is not what okay? As an engineer, I'm designing an embedded system that is real time. It's a weird statement, but this is the crucial one. You have to be able to cancel the signal if it doesn't happen within a certain period of time. That may seem like a really weird definition because it's not responding to the question, but it's really about if I tell it to do a command, can it respond in a certain type of command? And let me give you an example that will kind of explain why this is actually what matters to us. I need to be like with a regular computer, your command could get stalled by data or all kinds of other things and could get delayed in an unknown period of time. It could be all kind, you could be a low priority signal or whatever. Something could happen, delay it, and we don't know where it goes. Imagine I now hook this system up on the car you're driving. And I want it to kind of level my system or, brake assist or right? I'm just going to do level the system. You can imagine if I go in and as I go into the turn, naturally the weight shifts to the outside wheels, press them down. If you have a little more pressure, if you raise up the outside edge, you'll go through smooth. Your car will track better, it's smoother, it doesn't disturb the driver, lots of good stuff. So an active system, when you go into the curve, it's going to try to sense that and skip up the outside. to get a better response to the car through the turn. Well, what happens if it tries to raise up the other side of it a little bit slow? And so instead of doing it in the turn, it doesn't do it until you get out of the curve. Yeah, now if you get, right, you went down, you dipped the wrong way, so you're doing a curve, and then you get out of it, right? Starts jacking at the other, you're already returning back because there's no weight on it. You can actually cause the car to come out and get into this weird oscillation, and it can destabilize the car, it makes a crash. So if your commands to adjust the shift of weight between the wheels, doesn't happen when it's supposed to. It doesn't happen fast enough. And you can't cancel it when it's too late. Then you're gonna actually be more dangerous. Does that make sense? When you don't. The crucial issue is to have you able to break this. You can imagine a fire hit in the air. What if the command to adjust the fins so the pressure up and down or whatever hits too late? It's trying to stabilize some oscillation. You're a little bit out of phase. Instead of canceling the oscillation, you have to get the oscillation. What we really care about is you gotta make it happen when it's supposed to happen. So that's usually the big crucial area, and this is why you make these ones that they have times and intervals and this other stuff, because you're trying to be able to force, no matter what else the CPU is trying to do, it forces that the CPU has to deal with certain commands in a time sensitive way. So you issue the command and you issue a drop in with that command, and they have that. That's the really big issue. Now that ends up giving you what you want. It responds correctly in the time because it means, imagine if, you ask me for something and I don't get back to you for a week, right? That doesn't actually help you. You would say, I'm not being responsible. I didn't handle it, right? So I got to be able to respond with a certain time instant, and that gives you what you want. Does that make sense? So I think being careful. Some are complicated, right? There's what regular people mean, and you're special, right? You're an engineer. So you gotta realize we gotta bring weird vocabulary. Okay, digression, but I think an important one, particularly on the computer side. Okay, so real time is not as much necessarily my concern as I mean the engineering. Now, if you mean quick, then I totally agree with you. Right? This is the other, it is faster. Um, the clock slows you down. Most of your systems can actually do transitions multiple times in the period of the clock. Right? Because the clock is trying to slow it down to something manageable. I can go much, much faster than that. Now, this is actually a big issue for a number of other cars. What if I want a very, very fast system? Right? The synchronous systems are going to have limits. Asynchronous systems can go as fast as it is possible to go. And so you're kind of pulling all the safeties off. You have to make sure new problems will creep in. So we have to make sure we handle those. But it will give you super speedy responses.
And it can give more susceptible to like glitches, correct? So we can make like a glitch system.
You'll actually even get things other than glitches. Right, so glitches are those weird momentary transitions. We're going to get new things, race conditions, and all kinds of other stuff that can happen, where it will do behavior you did not expect at all. Okay? And that we haven't even covered how to deal with it because you didn't have to deal with it before. So we'll introduce some of these problems, what we mean by race conditions and things of that sort. We're going to have to design some, or talk about some new methodologies, how you identify them and how you design them to be able to prevent these weird other cases from happening. So, yeah, there is. There's got to be a where it's like, just think, fast and safe opposing goals. Yeah, exactly. You don't take a NASCAR, to drop kids off at school or go grocery shopping, right? But you're also not going to take a minivan to drag races. Yeah. unless you're like a really sick person who like replaces instant minivan or puts a really revved up engine just to humiliate somebody. But which actually is kind of fun to be able to. But that it's not going to happen. It's not a particularly great vehicle for that area. Again, safety, speed, different beasts. There are places we want safety. There are places we want speed. There is also reaction time. So I can have a very fast system, but that still could have little gaps where it just misses stuff. So asynchronous allows me to handle that as well. So these are special systems. Okay, that's kind of my big intro to it of why. Good idea with the basic idea of these. Okay, so let's go to everybody's. Let's get glasses on so I can see this paper. Okay, everybody's favorite startup system. Since I've already said it's everybody's favorite. Anybody remember what this is?
Two gigs, they input each other, and so I think it's significant, however, it's just what it does, but it first it's nothing is primary.
Would help if I label the signals. This is an SR match. This is the most basic bit of memory you can build out there. This is where all of the memory forms start off. And the key thing to remember, and this is actually a very helpful thing, whenever we talk about memory in any sense, we mean there's a feedback loop. So I heard some people talking about systems and things, right? So whether you're just talking systems or control, whenever you have memory, it has a feedback loop. Because that's what you need. You have to take the outputs to the inputs to be able to measure what the output was. So if you think about it, that makes sense. In this case, there's only one loop, even though there's two things passing down. If you would branch this kind of out, like I could take this one kind of a little forward, you could rewrite this. I could kind of take this line here feeding into this. All right, so here's S and here's R. Right? Oh. And then I could take this one feeds back around and comes in. So if you notice, there's really only one loop in here. So there's only one bit, one feedback loop. So you could make a smaller one than this. I mean, technically speaking, the smallest one that I can ever do is I can have a single thing. I could do whatever, an or, whatever I feel like. Right? This technically has memory to it. It's not particularly useful. That actually, in a sense, generates a clock, right? Because you're rolling zero as we can, and each thing goes faster and faster. It keeps eating up, and eventually the magic smooth comes out. So I'm not saying it's a great system, but there is some to this. The nice thing about what we have here is I have some controls that allow me to do things with it. So we can see that it's one bit. This is just like a little aside. Anybody remember how this system works? If you don't remember, so I'm just trying to probe where the edge of your memory is. This is usually the second half of digital logic. First half is combinational circuits, right? No memory involved. Then we go to these synchronous sequential systems, right? So sequential tells you sequence ID. That's what we sequentials. Well, let's walk through it. So one way to handle these is to figure out what its characteristic is. And this is a table. So this is a characteristic table. We know we have inputs S and R, and we're trying to figure out, I'm just going to do Q because Q prime should be the exact opposite of Q. All right. I'm going to start in the middle of this, right? Oh, let's take this line here, right? S is 0 and R is 1. There? Okay. Now there's some value to Q that's in here, but you'll find out it doesn't actually matter at this moment. Okay? S is, well, let's actually deal with R first. R is a 1. Ignore the not for the moment. All right? So Q prime or 1. It'll be a 1, right? It's 1 or anything is 1.
Yes.
Right? Naughty. Now we include the not. It'll be a 0. It does not matter what Q prime is. Right? Okay. Then we have up here. Now we have 0 or something Q, right? So that'll be Q. So for a brief minute or a brief instant, it could be a 1 if Q is 1. But pretty soon, because Q is going to become 0 and it ain't ever leaving, right? So if we just consider over time, Q is going to become 0. 0 or 0 is
0
and then negated is a
1.
1. So this is going to go to a 1. There might be a little transition time from whatever it had been.
Is the
So this is why we say there's a little delay is onto it because there's but once it does, it becomes this, and it's 101 on them. Yeah. So I could even lose that. That's going to stay there. So that's actually a nice condition. So if you're considering that the output is Q, Q prime, and when I assert on, I know that Q goes to a 0, right? And that's why we call this R for reset. Okay? It resets your system so that the output is 0, the negation of the output is 1. But it always is going to reset button, right? That's all back to 0. Make sense? All right. Let's consider the flip, all right? The SR. Now, let me ask you, does this look symmetric? It does. So I flip it, and the R line becomes the S line, and the S line becomes the R line, and Q and Q point. Does that make sense? You work the equations if you want. But if you notice the symmetry, you should notice if I was serving S but not R, then I should end up with 0 on Q prime and 1 on Q. Does that make sense? Because they're just flipping. Give me a thumbs up if you agree this is obvious. Please move on. So please move something. That's what we want. That means Q becomes a 1 in that flip case. So it becomes 6. So you know, and you see what each one so allows you to either we now need a way to get the value. What happens if I don't do anything? Both of these are 0. So I'm going to move this till let me find theirs. Okay, red. Fine. Oops, I showed you that. Let's say they're both 0. Fine. Now, I'm going to take this initial condition here. They're both 0, right? 0 or Q is what?
0 Q
Is 0 or Q is Q, knotted, Q prime. Right? Now, how about the other line for R, right? You get 0 over Q prime.
Which is one of these.
Q prime, and then mod
Is Q.
Q. So you notice what it's doing? As long as Q and Q opposite each other, and we go to 0, 0, it just preserves what it was before. Does that make sense? It's a kind of a quick and dirty thing, but if you understand what the dates mean, it makes total sense. That's only working if Q and Q prime are opposite each other. That's our stable case. So that's good, right? But we know that the result on this one, right, is Q prime. I'm going to use little q, right? Little q means either the current or the previous state, and big Q is the next state. That's what we're actually calculating here. Right? We're saying big Q, the output that's about to happen will be what it was before. A common shorthand is to just use capital Q for the output and little q for the previous state. You can also use, if you want, capital Q and use a sub P for previous and a sub N for next. Some people will do N and N plus 1 or N minus 1 and N, but that gets actually cumbersome to write. This is a really quick and dirty, easy one. Capital is the next state. The output will be. The lowercase version is whatever the current one is. There are a lot of conventions out there. This one's quick, dirty, and really easy to read. Right? All of those combos I find very helpful. When you're looking at something complicated, imagine you see the difference. What's the difference between these two versus seeing something like this? Right? The crucial piece of information you need when you're doing the capital small is right in front of your face, the previous. Whereas on the other one, you have to look at the full script and then so you're already getting small and it's a specialized area. It's just not as quick. So I just argue for this as I think it's a more readable format. And you're already dealing with something complicated, make the life easy. Okay. So far, so good? All right. Let's now go. I need one more. Here we go. Let's do this case. I like using different colors. That way, when you're looking at it, you can easily see what's happening. Now, this is essentially the case where I jam the turn it on and turn it off button at the same time.
If you anything is on.
Yeah. So this is the fun thing, right? One or anything is one negated zero. Right? One or anything is one negated stays zero. Just over color. Alright? So it's now 0, 0. So notice it's now violated that position. But is this electrically, does this make sense? Is there any it's not what you wanted in one sense, but really is anything going to freeze? No. Now the fun part is, so this is the thing, when people say, when you press that one button, you've gone into horrible space. It's not true. You set up a horrible space. It's like walking to the edge of a cliff. You haven't fallen yet. The problem isn't being at the edge of the cliff. The problem is falling off the cliff. So, by the same token, pressing the double one doesn't mean you can walk away from it. Once I press the double ones, can I do anything to be considered? It's wonderful. Care which one. I can reset and it becomes a reset condition. Reset condition, it can't be your memory thing was that. It will override something. It takes a little bit longer to set. But we're talking at most 2 cycles. And we're talking clock cycles now. We're talking how fast can the gate process an input cycle. So we're often talking in the picosecond, hundreds of picoseconds range. This is a very, very, very fast transition. So it doesn't take them long to switch. The same thing would apply the other. If I release reset and held set. So from the double press position, there are safe pieces. What happens? Pull the thing up.
If you pull time, you would get you get little, you get zero.
So let's look at that. I'm going to use green for that just so we know. So we're now at 0, 0 here, and now I go 0, 0. All right. So I've got 0 here and 0. 0 or 0 is
Zero.
0.
Zero.
Negated goes to a 1. Right. And on the other side, I had 0 or 0 negated gives me a, right? So they both flip from 0 to 1. Now I've got ones on these. Is it sufficient to do one of them? Because symmetry means it's going to do the other two. So 0 or 1 is a
Zero.
1 negated, and that's going to happen to both of them. What did I just make? Isolate. Now, are those two gates perfect? So do they transition perfectly? Could they be really similar? So you've got a frequency. What happens when you have two really close frequencies oscillating next to each other?
The two frequencies close to each other. It harmony.
Yeah, we call it a beat frequency. I mean, you get this little outer envelope, which is a really long frequency, right? You get this splitting. You get a really long frequency, and they're oscillating inside that, and eventually they can have a sync. I mean, 180 degrees out of phase, and back in phase. Do you know how long that is? Well, if you knew the underlying frequencies, you could calculate that. But we don't, depend on temperature. Faster they oscillate, the more heat they generate. So you don't even know what the frequency. You just know it's going to have a beat frequency, and they're going to be pretty similar. When they get far enough in range, it'll all of a sudden become 0, 1, and it'll latch. So it's going to oscillate really close together for an indeterminate period of time, and then latch. And do you know which one's going to latch? No, you don't. So it's going to oscillate like a crazy beast until it eventually randomly picks one from your perspective. You don't know how long it'll take to randomly pick up, and you don't know what the answer's going to be. Does this sound good? That's the danger. Okay? That's why we make this illegal. Okay? But it's not pressing one is the problem. It's releasing unsafely. You walk to the edge of a cliff and you look down, you haven't fallen. If you're smart and you step, you release one of the you're totally fine. You release them both at the same time. The race is on. You don't know which one finishes. So this is a first example of a race condition. Race conditions, you don't exactly know what the is, right? You've got two signals changing. There's a competition. And at some point, it's going to end something. But you don't know what that is. Right? That's the key thing with a race. Can I have a race if I'm the only one who shows up? No. I'm not racing anybody. A race, by definition, as far as we're concerned, is a competition. Two signals have to be changed. Right? And we're trying to find out which one gets to its final state first, like any other race in that sense. Right? In some cases, we might not even know where that is, right? Run until one of you gets sufficiently far from the other one, or whatever, right? You don't know what that is in this case. Then, yeah.
So you just randomly select randomly. So why can this be used as like a component of RNG?
So it's somewhat in, and people have used this for it. Here's the problem, though. It's not totally unknowable. So And this is fun. So a lot, you'll hear about these. If you look in the past, you'll actually even see like Las Vegas and all these have used this. But realize, if you use this as a random number generator, how tight something is will affect that oscillation. So, I could technically, by predicting the heat, and we do have temperature sensors on this chip, right? And that temperature sensor is on. And if we know, sometimes for a particular chip, at a certain temperature range, it will always go to either 0 or 1. It's not perfectly 50-50 at every temperature range. And so people have noted that it goes one way or another. And that's how they can start predicting your encryption scheme, your random number generator, or stuff like that. There have actually been arrests by engineers who are part of the design team who actually figured out how the random number generator did it based on the temperature. They carried a thermal measurement device or put it outside of a plain slot. When it got to the right temperature, they induced the case for it to go to win a really big slot. Right? And well, people have won millions that way. But you're not really, it's not a random competition anymore. You rigged it, so it's illegal, and they've gotten arrested because it's not like that can't be figured out. Suspiciously, some weird input came in, and a guy who designed this won $10 million. Oh, I wonder, right? So it's actually listed as illegal, but you can imagine I can do the same type of thing on encryption algorithms, and I can break into people's stuff or all kinds of other things, yeah.
Security means like generate stochastic numbers.
This is the great area, right? So it's, unfortunately this one does have some correlation. It's really hard to say what, but if you measure it, you can find these correlation probabilities. But this is true with almost anything, right? Some of your best numbers are environmental things. So what they started using was radioactive hits. Right? So what's the atmosphere? That sounds awesome. Unfortunately, that one too. This is another one that came in slots. Right? That means if I carry a slightly radioactive but known value, right? So I go like the smoke detectors, have a small amount of radium. Right? If I have a known quantity of that, I can know the exact weight things are hitting at, which means they're not going to see. So people have carried those in the keychain with a low value, and they put it next to where they know that answer is, and they've done it. The encryption thing, people have actually built a system that memorizes or detects the temperature. It's got a known which way it's more likely to flip, and they break people's encryption for sending data across, and store credit cards, and all kinds of other stuff. Right? So this is one of the great challenges, and this is why you kind of do have to understand what's going on in the system, because there are implications. And I'd love to say there is a perfect answer to this, but the reality is there isn't. You've got to get something that's sufficiently complicated. Why do these external keys that people plug in for radio generation work nicely? Well, because you're not able to get some of those measurements. Right next to them, and then you can cheat like that. Right? It's sticking and it's breaking. So all of a sudden, those key fob random number generators become actually completely, not it's completely deterministic. You will not find a perfect system. And when you're doing these type of things, you got to find something that is sufficiently complicated that it becomes too tough and you prevent people from getting cheat information. But if there is a way to do something, somebody's going to find a way to cheat. Right? Right? It's just the way it is. And sometimes that person's not even a bad person. Sometimes it's a good guy trying to protect somebody. Yeah. You're trying to rescue a kid who had been kidnapped, and the information you need is encrypted on a disk. Somebody learning how to cheat, and that saves the kid's life. Oh, good. Good guy trying to cheat and the system. I mean, there's no way you can handle all of the situations to do it. So therefore, as an engineer, the only thing you can do is design the best, strongest system. You do what your design thing is for, because you cannot handle the rest. But you do have to think about it. these type of things. Does that make sense? This gets into a little bit of ethics. But the best thing you can do when you don't know any different is to handle it. Right? Realize there are cases like that, one of the good guys trying to shoot the kid. This is why the government always petitions to try to have a way to break into any particular code that's out there. That's their case that they make. Do you think that is the only case they're going to use that particular thing? Right?
People cheat, so they heard
So government is made up of a bunch of people, so do you think the government cheats and does some scummy, sleazy things? Yes, they do. Do they have a good excuse that people are going to buy to give them power to be scummy and sleazy? Well, they sometimes use it for the good thing. Well, they sometimes use it for the bad thing. Well, probably to both of these. You cannot solely determine what that is, right? This stuff has to get hammered out, right? Professional societies determine ethics and make standards. And societies, debate these things out and create laws on what this has to be. As engineers, we have to design to what the ethical standards of our profession and the legal requirements of the country. You cannot pick your own route. But you should be aware of it, and if you see a problem and you think there's a problem, then you appeal to the right authority. And you appeal to the one that you know is going to give you the correct answer. In some sense, you will know what that is. You'll see really, and more often than not, the professional society will give you the ethical answer because they have the answer. Any group has an outcome they want, it will skew, right? Even if it's overall a nice government. Nice government still do scummy things, right? This is just reality, right? There's no perfect solution to these. Somebody who doesn't have a vested interest will give you a more impartial one, and therefore more likely to get something that is ethically fair. So more often than not, your professional standards will stop to appeal. And in most cases, most governments will recognize, a professional society standards. Right? They may not like it, they may appeal against it, and all kinds of other stuff. But generally, I would suggest your first line is to appeal to that. I don't say this from abstract. I've been a design engineer actually 6 times in my career, both as a design engineer and as a had to appeal something. You will run into it. It's going to happen. So just be aware of these things. Do the right thing. If you feel something is sus, note it first. You go, hey, something seems weird. If they're not responding correctly, make the appeals the line. Right? Jumping appropriately to professional societies or whatnot as needed. Right? It is an important thing. In the end, you will not be able to sleep if you did something that is immoral. Right? As a decent human being, it will bother you. Right? Yeah. So that's crucial. This is just one of those many areas that kind of hits on things. So we make this illegal. Jumping back, right? And again, it's not that the problem happens when you push them, it's when you release them. And how you release them changes the output. Fair?
illegal in terms of like code.
Yeah, you're not allowed to do it. Right? And everybody realize legal doesn't mean impossible. Illegal means you're not supposed to do this. Right? You're not supposed to jaywalk. Does that mean if you jaywalk across the street and an invisible person puts you back? Yeah, right. It's a rule that you should avoid it, right? So your designs are supposed to avoid this case because it creates a potentially dangerous spot. We want the speed, but we don't want the danger line. Right? So that's what this is. This is illegal to you. Right? It's like if you were taking kids to the Grand Canyon. You say, don't climb past the fence. Right? The sign doesn't prevent you from climbing past the fence. right? It just lets people say it. They earned the dollar. Right? So, it's wrong, but it is wrong, right? But that's where the difference between illegality and, having a natural enforcement mechanism. Realize really good engineering design to actually enforce things by nature. This is one of those areas I like to use as an example. How do you put in legal codes to try to prevent something bad? Like, do we like polluting rivers? Is it advantageous sometimes for companies to pollute rivers?
Yes.
Right? So now you have to have people who monitor all these things to make sure they're not doing any stuff. So there's a famous guy, I can't remember his name, who's really well known for making things that have natural enforcement mechanisms. There's no need for somebody to go. In that particular situation, what he said was he created and petitioned for this law, got the law passed, where the input from your plant has to be upstream from your intake. So if you pollute, who's stopping it up first and most concentrated? You are. What does that do to your plant? It's a huge hit. That's really expensive. This is a self-enforcing mechanism. So there are things like that where the legality is kind of enforced by nature. And what they discovered is everybody became compliant really fast. Because the alternative was pay lots of money to destroy your own stuff. I mean, yeah, yeah. Those are always very smart conditions. This is just illegal. I don't. Right? Not impossible. Okay, we're good? All right. So let's go in and start doing some kind of quick designs with these things, right? So this is a latch. Realize it transitions whenever the heck it wants, as fast as it wants. But it can hold memory. Okay. So let's say we wanted to take this and we wanted to build something that did a basic, we have a count signal that comes in. So this is an input. And we have our current state, which is little q. And we all know what big Q is. So very simple system, right? And we'll eventually want to figure out what SR is. So let's take a look at a basic. Let's say if count is 0, right? No matter whatever Q is, I want big Q to be whatever that is. I want to hold if C is 0. That means don't count. Or don't toggle, whatever you want to consider it. All right? Let's say if I put count to a 1, whatever Q is, I want it to flip. Now, if you change this C to a T, this is a T latch, if you've ever heard of toggle latch. But this also is doing what we count. This is the first stage of any counter that you might have, right? Because it flips them, and then we can use that flip to determine something else. So this is a very common single bit system that's going in. So far, so good? Okay, now we want to determine from this, can we figure out what is SR, right? So what this is, in a sense, if we look at this, we're trying to build something, right? We call this next state logic, which is going to output S and R. That's what saying an output is for this next state logic. That will then go into, I'm going to just kind of box this whole thing, right? And I'm going to just call that my SR latch. So it's going into an SR latch, and it has, I'm just going to show Q coming back around. Q prime is obviously related to it. Capital Q, this goes to little q, and I have an input C, right? I already know how to build an SR latch. It's fixed, right? So all I'm trying to determine is, based on what its current state is and what C is, what should I tell S and R to do to make it do this transition table? Does that make sense?
So what's the current module?
So this right here is what we call next state logic. It determines right? This table specifies a particular logic of what the next state should be, right? If C and Q are both 0, the next state should be 0. So what should I pick S and R to make the next state 0? That's what we're asking. Okay, so that's what we want to get to. And what we want to do is build a consistent method for doing this. Does that make sense? Now we have what we call a characteristic table up here, which tells us if you know S and R, what is going to be Q. We ideally almost want the reverse of this. We know little q, and we know what we want for big Q, but we want to know S, so we want to flip the table. Does that make sense? Okay, that would be most helpful. Otherwise, you're going to have to do that, think it through every single time. So we'd like to be able to say that and say, hey, can we say, knowing what we want, what it should be? Good? Okay, we're going to call that the excitation table. All right, that means I know what I currently have, and I know what I want, and I would like to know what SR will get me there. So far, so good? We're going to figure out this table, and then we know little q and big Q, and we can immediately write the SR. That makes sense? This just makes it easy. Confused. You could work it out every single time, but now it's dependent upon me thinking correctly every single time. Since this is a very consistent method, it's easier to build a table. There's only 4 possibilities. Figure out what the result is, then you could just go to the table and go, I know little q and big Q, find it in my table, and it will tell me what SR should be to achieve that. That's all we're saying we want to do. We already know that we want this to generate this. So we know this to here. We just want to find this middle state. Okay, so let's put our possibilities. Now it may look a little weird, but I'm going to write it this way. And again, the reason is it's just a little easier to read, I think. When you write it the dense way, it's just a little bit harder. Okay, so we're going to take a look at our characteristic table. I want to go from 0 to 0. Now, let's think about how many ways I could do this. Could I do this, where I hit reset but not set? Would that achieve my end goal? Yes. Is there any other way to do it? Well, little q is already 0, so this is also a 0 in that. So I could also turn S and R both on. So S has to be 0 for this case, but R, I don't care. X meant don't care. It could be either one. So as long as, S is a 0, R can be whatever makes you happy. It doesn't change things. I've got some design freedom here. Let's say I want to go from a 0 to a 1. Right? Well, I can assert S. Is there anything else I can do? So little q is 0, so my table looks like 0, 0, 1, don't you dare. Okay? Right? That's what I'm saying, don't you dare. Right? It's not impossible, but don't you dare. That's, so how many ways can I become 1? Only one way, right? I have to do my 1, 0. Here in this case. Okay, what if Q is 1 and I want to go to 0? 0, 1. Yeah, it's the only option, right? Because little q is now a 1, so it's a 1, 0, 1, don't you dare. Okay, how about the last one? 1 goes to 1.
Q, say,
Yeah, so I can do yes, right? Well, close, right? Because it's this 0, 0, or it's this 1, 0. So that's a 0 here, but the don't care. Now, the neat thing about most of these, if you notice, the table is symmetrical. You see it? If you kind of reflect through the very center point, right? The X goes opposite corners, or you can see it's mirroring to a point. Right, so that makes it nice for remembering. But the key thing is it's called an excitation table. You can look it up. Yeah.
So is this an example where you
Yeah, you have you have an X there, which means you can count it as a 0 or 1. Whichever one is easier for you on some. Sometimes it's better to do 0 and sometimes it's better to do 1. But you can look at the pattern and kind of pick it at that point. That's why it's nice to have the X, because it's your option. What makes it easy? And you pick it the way you want to make a bigger encirclement or less encirclements. All right, so far so good? Yes. Okay, so now we're just going to do it, right? I want to go 0, 0. That's my transition, right? So I come across and I go 0, X. I want to go 1, 1, right? So that's X, 0. You guys help me with the next one. What do I do? 0, 1. So what do I, 0, 1. So I want 0, right? Yeah, then I want to go 1, 0 here. So it's 0, 1. Boom. That is what I need to do for next state logic to turn this SR latch, which is really stupid fast, and I'm building combinational logic here, so it's going to be really stupid fast. There's no clock in any of this. So I have now built a system that meets your requirement. That's really stupid fast. You don't handle all those transitions and everything else. All right? So let's actually do it. All right, so now I need to do a design here. Now there's several ways I could do it, right? We could do K-maps, we could do all kinds of things. I could also just look at this. This is kind of a recognition thing, right? So you could kind of recognize this. Anybody recognize, if I made this X a 1, do you recognize that pattern? 0, 1, 0? Oh, that's exclusive OR. Right? So I could just look at this and go, ooh, I can make an exclusive OR. And what does this look like? Exclusive OR, right? If you make that X a 1, right? That's pretty nice, right? I can do this with a single exclusive OR gate, right? Because all I have to do is don't negate the output of the XOR or negate the output of the XOR. And that can be done in one gate. It's kind of nice. Is there any other way I could do this? Do you see any other patterns? Yeah, so what if I made these X's zeros for a second? I only have 1, 1, right? If you have a single 1 output, that's an AND gate at some level. And you may have to flip the inputs or whatever. And R is just directly, right, taking C and Q, right? And this one is just, right, C and Q prime. Well, Q prime is a freebie output. I don't even need a gate for that. So I can also do that. So these, realize, I don't always, particularly when they're small, I don't always have to do it, Katie. You can just look at it. And so, you can kind of take it from there. Let's do it real quick both ways. I have 5 minutes, so we can do real quick. I could recognize this as an XOR, which means that S has to be, right, C exclusive OR Q. That gives me this. 0, 1, 1, 0. Right? And R would be this negated. Right? So R would be equal to C exclusive OR Q prime. If you also like, just as a side note, this is also the same as C equivalent to Q. That's what that one is called. And it's saying when C and Q are both the same. And if you notice, when they're both C, we're both equal. So that's also called equivalent, if you're so interested. And most it is exclusive or negated. So far, so good? Anybody remember what happens? Well, this is the right interpretation when you're only dealing with 2 bits. What happens if you go like 3 bits?
You have 3 bits.
Yeah. How do you understand, or 4 bits, or 5 bits? What does exclusive or tell you at that point? What's the right way to understand?
So or means that only 1 bit is long. It's
Only one.
No. So and actually, exclusive or will also hit on the raw one for 3.
Oh, so it's common for
It's off. That's an odd number of inputs on. That is the correct answer. And the quib means an even number on. So when you extend the higher things, that's the correct understanding. Even a number of bits on your input. Just a side note, but you ought to, these are shortcuts to remember it correctly. And it also helps sometimes you are looking for odd or evens. I mean, then you can do it in a single gate if you understand it. All right. So this tells me what that is I can just build this, and I have built my next state logic. So both of these use an exclusive or, and I have C coming in, and I have Q coming in. And the exclusive or, I just fork it to come out, and this one is S, and then I negate it, and that one is R. Now, is that going to have the exact same kind 2 lines? Is that potentially dangerous?
yes.
Okay, so what we could do, and if you ever wondered reasons you would want to put a buffer, I could put a buffer that transitions in about the same time as that normal, so it creates an almost identical and match as well as I can. So that I get that. So now the signals are getting as close as I can make it to them. Does that make sense? And then you could just take this and I plug it right here, and you now have a functioning system that's asynchronous. That makes sense? And I could obviously, I submit to you, try on your own to do it with just the AND gates, or whatever you want. Try it one other way on your own and see if it works. Okay? Hopefully that makes some sense. The other thing that we will often do for these is we'll take a look at these and we'll say based on the, whatever the inputs in, what are stable, i.e. it stays the same. It's in a memory. So we'll often say this is stable and that's stable because it's not changing, but these are not. And, and we can look at those and say, okay, what could happen with these? And that's where we take a look. What if I made these all zeros? Right? Well, what if I made this a 1 0 here? Right? So to go from this to that, right? I now have to flip both of these. Does that make sense to the thing? Well, what if I hit it slightly out of sequence? If I flip it perfectly to 1 0, I'm okay. Right? I'll still get down to here. Right? But what if I don't? What if I accidentally flip it to, in going to 1 0, what if I go through 1 1? Which is my danger situation. I could end up with getting a weird value I didn't expect. So races, I want you to realize, are not just inputs. It's any 2 signals. It's all the one-sided. So this is one of the things we're gonna deal with next time. We know race conditions and all kinds of other things. But realize I put on these. This is something else you need to consider. Where from here, then you're going to want to switch. You want to think about those flips. So I don't accidentally get 2 signals racing and one get SRIs before. Because So to change things, I like things to have, you know what the outcome's going to be. So that becomes an issue. And then how do we analyze that is recent issues. And that's what people do next time. Do we feel comfortable with asynchronous? Why it is, right? I can still use my combination design techniques you've been working on, right? SRI just make it a little bit easier, right? But it's flip flops, you still get that speed, but there's more consistency, and you can use these characteristic tables to do analysis. And that's citation table to do to how the two runs. Everything feel good? Next time we'll look at some of these. How do we handle things? Then we'll get into things like state reduction and all that fun stuff. If you've got questions, as always, please come up and I'm happy to answer what I can. Otherwise, have a lovely day.